Hello students, today we will start with topic number 9.6.2, determination of Young's modulus of the material of a wire. Students, we have already studied about the Young's modulus and also obtained its formula. Now experimentally how we can determine the Young modulus of any given wire, that is shown here. Here you can see in this figure that there are two wires A and B. They were supported at the ceiling, and here this wire A is known as reference wire, and this wire B is known as experimental wire, the wire of which the Young's modulus is to be determined. Now the wire which is used here is having a uniform cross sectional area. Also you can see the scales are attached here. Here on this reference wire a main scale is attached, and to this experimental wire there is a pointer as well as there is a vernier scale fixed with it. Also you can see at the ends of this wire there are pens suspended so that the weights can be kept inside the pen. Now here in this reference wire some weight is placed inside a pen, and due to that what will happen, there will be a force in the downward direction, and as a result this wire reference wire will remain stretched, means it will remain straight. Otherwise what will happen, if there is no mass inside the pen, then the wire will not remain straight, it will remain like this, curved. But when the weight is suspended, what will happen, the wire becomes straight. So just to keep the wire straight, some mass is kept inside this pen. Now initially some mass is kept inside the pen of this wire B also, so that this wire which is experimental wire that becomes straight, but that mass has not to be considered. After that, gradually when the masses are increased inside this pen, what will happen, the wire will get stretched and its length will increase, and that increase in the length can be noted with the help of this pointer attached with a vernier scale. So stepwise we have to put the masses in the pen and obtain the change in the length of this wire with the help of this scale. So now students, it is clear that as we have studied that Young's modulus is nothing but it is stress upon strain. Now what is stress? Stress is force per unit area, and strain is change in length upon original length. But what is force here? Force is due to weight, and weight is equal to mg, where m is the mass in the pen. And so putting sigma is equal to F by and epsilon is equal to delta L by L, but F is equal to weight, which is mg. So in place of F we have kept mg. This L will come to the numerator. Area A, this area is cross sectional area, so it is pi r square and delta L as it is. So we get this equation for the Young's modulus for a given wire. Now putting all these values obtained from the experiment, we can calculate the Young's modulus of any given wire. Now topic number 9.6.3, shear modulus, denoted by G. Students, whatever the modulus is, Young modulus or shear modulus or any other modulus, all the modulus has the unit of stress only. Now about this shear modulus. Again, any modulus is stress upon strain only, but here it is a shear modulus, so this stress must be a shearing stress, and strain is also shearing strain. And what is shearing stress and shearing strain? That we have already studied. Now shearing stress, force per unit area, and shearing strain is delta x upon L. Students, you must have remember, suppose there is a cube and if a tangential force is applied, so what will happen? If this part base is fixed and if the force is applied at the top, then this type of change will be there in a body. So this much distance, the shifting of the upper face is nothing but it is delta x. And cross sectional area, this cross section area is nothing but it is this area at which the force is applied. So students, delta x upon L is the strain. This can be written as like this, FL upon delta x into A. Also, we know that shearing strain is nothing but it is theta, the angle it makes here. This is the example of that only, shearing stress and shearing strain, that is modulus, shear modulus. So here you can see this angle is nothing but is theta, and this much displacement, that is shifting of the upper face, is nothing but is delta x, and the force is applied here along the tangent to this cross section. So length is considered for this, and also this is the thickness of this given slab. So length into thickness will give the cross sectional area. So strain is equal to theta, and so in that case we can write the shear modulus G as force per unit area upon theta, and that is equal to F upon A theta. Shearing stress can also be expressed as sigma s is equal to g into theta. Students, directly see here in this equation. If I'll put theta in place of epsilon s, and if I make the subject shearing stress, then what you will get? You will get g into this theta. Unit of g is Newton per meter square or Pascal. Any modulus has this unit only, whether it is a Young modulus or Scher modulus or any other modulus. Now example number 9.4. Here a square lead slab is given. You can see that in figure, whose length is 50 centimeter, that is shown here, and its thickness is 10 centimeter. You can see the thickness here, and the force applied, you can see a tangential force. That force applied is also given, which is 9 into 10 raised to 4 Newton. Here we have to consider that this face, that is base of the slab, is fixed, and so if we apply force here, then what will happen? It will deform, and so now this upper face will slide a little, and so there will be a change in the angle. Earlier this line was here, this is the initial condition, but after applying the force, this line will shift by this much distance, that is delta x. So some angle is formed here, and remember students, this angle will be very small. It is very difficult to identify that angle also. So to identify this angle, we have to use different techniques, experimental techniques, because you can see here this angle is nearly 2 degree, but actually this angle will be very less than, even it is less than 1 degree also. So no much change will be find in this. So angle is very small. Now here we want to find the displacement of the upper edge, that is delta x, and for a lid, shear modulus is 5.6 into 10 raised to 9 Pascal, that is given in the table 9.2. Even in the exam or test, this value will be given to you. Now let us start. We know that shear modulus G is equal to FL upon delta x into A. From where we obtained this? So it is here. So students, here this area is the cross section area at which the force is applied, that is this is the area of cross section. Now just make the subject delta x in above equation. You will get FL upon GA. Force is given, length is also given, G is also given, but cross sectional area is equal to length into thickness, and both this length and thickness are given to us. But remember students, these are given in centimeter, so when we put the values, we have to convert that into meter. So I have kept here all the values. This is the value of F, this is the value of L, which was 50 centimeters. So I have converted into meter. Value of G, then value of L, and into value of T. You can see both are converted into meter because they were given in centimeters. Now after a simple calculation, you will get this delta x is equal to 1.6 into 10 raised to minus 4 meter. Same thing, you can write this into mm, and that you know how. Still, I'll show you how this is 0.16 mm. Students, 1.6 into 10 raised to minus 4 is given here. That can be written as 10 raised to minus 1 into 10 raised to minus 3 meter. But what is 10 raised to minus 3 meter? This can be written as mm, and 10 raised to minus 1 into 1.6 means 1.6 divided by 10, because 10 raised to minus 1 means it is divided by 10. So this can be written as 0.16. So 0.16 mm. Now about bulk modulus, denoted by capital B. Topic number 9.6.4. Students, according to this statement, that is the ratio of hydraulic stress to the corresponding hydraulic strain is called bulk modulus. Symbolically, we can write B is equal to hydraulic stress, or you can say volume stress, upon hydraulic strain, or you can say this as volume strain. And what is volume stress and volume strain? That we have already studied in our previous chapter, previous topics. So B is equal to sigma V upon epsilon V. Unit of B, as usual, whatever the modulus is there, its unit will remain same only, which is nothing but the unit of stress, because there is no unit of any strain. Strain does not have any unit. Now hydraulic stress is nothing but it is pressure, that also we have studied. And here volume strain is nothing but it is change in volume upon original volume. Now students, why there is a negative sign? It is because when the pressure is applied, volume decreases, and so this negative sign indicates that the volume decreases when the pressure increases. Or reverse case, if the pressure decreases, then volume will increase. So this P and this, they have opposite natures, and so there is a negative sign. And so to keep this B, that is bulk modulus, positive, because bulk modulus is always positive, so to keep this positive, we have to put a negative sign here. So this negative sign makes this value positive. So now simply just put P in place of sigma V and minus delta V by V in place of epsilon V. We will get B is equal to minus P upon delta V by V. Remember this, bulk modulus is always positive. Now compressibility denoted by K. Symbol is small k. The reciprocal of the bulk modulus is called the compressibility, that is inverse of B. So K is nothing but it is 1 upon B. In other words, we can define this as the fractional change in the volume per unit increase in pressure. Change in volume, but that is fractional change, that is delta V by V per unit increase in the pressure, that is upon P. So delta V by V upon P is nothing but it is compressibility, which is nothing but it is inverse of this. Now the bulk moduli of any solid are much larger than that of liquids, which are again much larger than that of the gases. Students, solids can be compressed much more than that of liquids. Liquids are very less compressible. If we apply the pressure on the liquids, then its volume changes very less, which is negligible. But if we apply the pressure on the solids, then their value of volume will decrease considerably. But for gases, if the pressure is applied, then its volume changes in a large amount. That means gases are highly compressible. Students, if suppose there is a container filled with a gas, so this container consists this much gas having this much volume, that is its volume will be that equal to that of container. If I want to put all these gases which are in this container, large container, into this small container, then I can fill this gas inside this much container also. That shows that this is highly compressible. It can be compressed and that can be filled into this small container also. But think that if there is a bucket filled with water and a small tub, so can I fill all this water of this large bucket into this small tub? So it is not possible, because liquids are very less compressible, but gases can be filled into a small container. When the high pressure is applied, the gases they contract at a large amount. Solids can be compressed but not that much as gases. So remember students, liquids are very least compressible and gases they are highly compressible. Now example number 9.5. Here given that the average depth of Indian Ocean is about 3000 meter, means it is 3 kilometer. This is the average depth of Indian Ocean. So that depth is denoted by H. Now the water which is at the base, it is compressed due to pressure of the upper water. Suppose this is the base and this is the surface of the ocean. So we know that the water which is at the base, they have a pressure of the water which is on it. So due to that pressure of this upper water column, this lower water, they are compressed, and so their volume is decreased due to that pressure. So here this type of concept is given. Given the bulk modulus of water, a that is equal to 2.2 into 10 raised to 9 Newton per meter square, and G acting is 10 meter per second square. We have to take value of G this much. Also the density of water is given. Actually it is not given in the statement, but always density of water is nearly 1000 kg per meter cube. Actually this is for a pure water, and we know that sea water is a salty water, so its density is little different from this. But here we will consider the density of this sea water as the same as that of pure water at standard temperature and pressure. Now here our aim is to find the fractional change in the volume. So starting with the bulk modulus, because B is given, so we will first write the equation of B, and we know that it is pressure upon fractional change in the volume. So now just make the subject delta V by V, we will get P by B. Now look, B is given, but pressure P is not given to us, but we know that pressure P is rho GH, where rho is the density of water, G is the acceleration due to gravity, and H is the depth. So in place of P, we have kept rho GH. Students, once again, this is the base water, and suppose this is the level of water, and from the base, let it is having the depth H. From the surface, this depth is H, and we know that water particles which are here, it has a mass m, and to every mass G is acting on it, and so here pressure is given by rho GH. Rho is the density, and density rho is nothing but is mass upon volume, because the water column which is above the surface has some volume, and that volume will have some mass, and so mass upon volume is nothing but is density. So this concept is used, and so we have to consider this pressure as rho GH. Now putting the value of rho GH and B, and then calculating, we will get the change in volume, that is fractional change, because it is delta V by V. So this is the fractional change in volume, which is equal to 1.36 into 10 raised to minus 2. And therefore percentage compressibility, this is compressibility. Fractional change in volume is nothing but it is compressibility only, and if we want to find the same thing in terms of percentage, we have to multiply this by 100. So if we multiply this by 100, then this will cancel. So what is remained? 1.36%. So you can see this 1.36% is a very small compressibility, and so we can say that water which is a liquid is a least compressible. Now Poisson's ratio. This is the name of the scientist, name or surname of a scientist. When a tensile force is applied on an object, its length increases, but the dimensions perpendicular to the direction of the tensile force will reduce. Students, in Young's modulus, we have seen that suppose if there is a linear rod, metallic rod, if I'll apply the force, what will happen? Its length will increase. Definitely its length is going to increase when the tensile force is applied. But if the length increases by delta L, then definitely this cross sectional area, earlier it was thick, now it will become little thin. So while obtaining this Young's modulus, we have not considered the change in the cross sectional area. We have considered that the change in the cross section area is very small, so that can be neglected. But actually, when the wire is stretched, its length will increase and its cross sectional area will decrease. And so here arises a Poisson's ratio. And so here it is written that length increases due to tensile force applied, but there will be a reduction in the cross sectional area. When the length increases, the cross sectional area will reduce. So this was studied by the Simon Poisson, and he pointed out that within the elastic limit, lateral strain is directly proportional to the longitudinal strain. Lateral strain means strain which is produced due to change in the cross section. You can see in this figure the earlier cross section, when the forces were not applied, the cross section was more, and when the force is applied, the cross section reduced. This wire or a cylindrical object will become thin, so lateral surface will become reduced, and due to that a lateral strain is produced. This here, due to change in the length, there will be a tensile strain, but due to reduction in the cross section area, there will be a lateral strain. And so the ratio of the lateral strain, that is lateral means sidewise along the curved surface, we can say sidewise means curved surface, that is lateral. So the ratio of the lateral strain to the longitudinal strain, longitudinal means along the length, that is longitudinal, and along these sides, that is lateral. So once again, the ratio of the lateral strain to that of the longitudinal strain in a stretched wire is called Poisson's ratio. And so it is clear that the longitudinal strain is given by delta L by L, that we have studied. And now lateral strain, what will happen? Earlier diameter of the cross section was large. When it is stretched, the diameter will decrease. So change in diameter to the actual diameter. So it is the ratio of this. This is called a fractional change in diameter. This we can call as fractional change in length. So fractional change in length upon fractional change in diameter is nothing but it is Poisson's ratio. Poisson's ratio can be denoted by this symbol mu. This symbol is not given in your textbook, but we can denote this by mu, and it is delta L by L upon delta D by D. Longitudinal strain upon lateral strain. Now, once again here there is a negative sign. This negative sign indicates that when the length increases, cross section will decrease. Here there will be a negative sign. So length increases but cross section area will decrease, that is diameter will decrease. So there is an opposite nature. Students, one more thing. If you will apply the force like this, that is compressive force, then what will happen in that case? Here this length will decrease, so this will be L minus delta L. But in this case what will happen? Here the cross section will increase, diameter will increase. If you compress the cylinder or a wire, cylindrical wire, what will happen? Its diameter will increase, so here there will be plus in that case. So always these two are in opposite nature, and that's why there is a negative sign. So this negative sign makes mu positive. Now topic number 9.6.6, elastic potential energy in a stretched wire. Students, in a solids we know that there are atoms and molecules. These are bound by some forces. So there is an interatomic forces inside this material. So when the force is applied to increase the length of the wire, suppose when this force is applied, there will be change in length of delta L. And so this change in the length is against this force, interatomic forces. And we know that for that we have to do some work, because force into displacement is nothing but is work done, and this work done is against the interatomic forces. And when we do the work, that work done gets converted to the potential energy of this wire. So I have written here, when a wire is put under a tensile stress, work is done against the interatomic forces, and this work is stored in the wire in the form of elastic potential energy. Now students, whenever there is a change in length of a linear object, there always present a Young's modulus. So here also there will be a concept of Young modulus used. Now here let us consider a wire whose original length is capital L and whose cross sectional area is capital A. And when this wire is subjected to a force F, we can write Young's modulus Y is equal to FL upon A into small l. Now what is this small l? This small l is nothing but is change in the length. Generally we used to denote delta L. If the actual length is L, then what we used to denote change in length? Delta L. But here this elongation of the wire that is change in the length, is considered small l. So we have written this Young's modulus. Now we know that there will be a force, interatomic force, present due to that change in the length, and that force F is equal to YA upon L into small l. This is the change in the length. Students, this Y, Young modulus, for any given material is constant, and you know that when we consider the Young modulus, we consider this area as constant. We consider that the area has not been changed. Actually, we know that there is a small change in the area, but here that area will remain constant. Original length, that is also constant. So here these terms are constant. So when the force increases, this L also increases, and if the force decreases, then this L will decrease. So there will be a change in this small l only with the change in force. Also, when I say I have applied the force on this rod, then what will happen? The interatomic forces will be in the opposite direction, having the same magnitude to that of the external force. So this is the interatomic forces or external force, whatever you consider, because both are same. These two are equal only. Now, the work done for further elongation. Already we know that suppose some force is applied, and for this force the elongation is L. Now, if a further force is applied, that means if the force is increased by a little, then we know that this length will also increase. And so here written that the work done for further elongation dl, that means the change in the length. Now once again, when the force, a little force is increased, the little change in length is divided by dl. So this much length was changed. But for very small change in the length, we can consider that force as constant. And so for that change in the length, the work has to be done. And that work done is dw. Small work done for small change in the length. And for that small change, we can consider that force as constant, which was shown here. So if we want to find the total work done for increasing the length from original length to L plus L, that is small l is nothing but is delta L, that is change in length. We can write this as from zero change in the length. That means initially suppose force was not applied, so change in length was 0, and after application of force, suppose the length increased to L. So suppose if you want to consider that the length is increased from 0 to L, the total work done can be obtained by integration. So if we integrate this, we will get the total work done. So I have written this total work done is equal to integration of dw. And what is dw? It is fdl. So fdl. And we have to put the limits that when the force was applied, the length was increased from 0 to L. But what is F? F is this from equation number 1. So putting that F from equation number 1 and taking out these constants, as I said, these are constants, so that are taken out of the integration. So what is remained in the integration? This. L and dl. Now integration of L dl is L square by 2. These are the limits. So initially in place of L we'll put L, minus in place of L we'll put 0. That is upper limit minus lower limit. And so we will get half of YA upon L into L square. Now this is the work done. This can be written in this way also. Look here, 1 by 2 as it is, this Y as it is, A as it is, L square as it is. What is remained here? Only L. So now what we have done here? Actually there should be L only, but we have divided by L and multiplied by L. So here in the denominator there will be L square. So I have written that in this equation we have multiplied and divided by L. So we got this. And why I have arranged these terms in this way? It is because we know that this length into cross section area can be written as volume. L into A is nothing but is volume of that wire. Once again students, look here. Suppose this is a wire having length L and its cross section area is A. So area into length is nothing but is volume of this wire or a cylinder. And that's why this L into A is nothing but is volume. And what is L by A? This small l is nothing but is change in the length. So change in length upon original length is nothing but is strain, longitudinal strain. And here there is a square. So we can write this as epsilon square. It is a longitudinal strain. So work done is nothing but half of Young modulus into strain square into volume. And this work done is stored in the wire in the form of elastic potential energy. This work done is nothing but it is the elastic potential energy. That is W is nothing but it is U only. So we can write U is equal to same as this. Now elastic potential energy per unit volume, that is energy developed per unit volume, denoted by small u. So what is small u? It is energy density. We can use another word as energy density. So u is equal to total energy upon total volume, and that is equal to this. Simply what you have to do, see, this is total energy and you have to bring this volume here. So it will be u by v. So what is remained here? Half of y into epsilon L square. So here I have written this term in this way, see, half of y and epsilon square, but I have written this separately. It is because now Young modulus into epsilon L is nothing but it is stress, and this is strain. So we can write this as half of stress into strain. Students, once again we know that y is equal to stress upon strain. So from this, what is stress? Stress is y into epsilon. So here that's why y into epsilon is nothing but is stress. And so we can write this energy density, potential energy density, as half of stress into strain. So this is the concept of elastic potential energy. Now about applications of elastic behavior of materials. Why this elastic behavior of material is studied, for what is it important, where the concept of this elasticity is used, that you can refer in the textbook. So here applications of elastic behavior of materials are given. Students, generally in all engineering designs, the concept of elastic behavior of material is considered. We know that the cranes which are used for lifting heavy loads, they use the cable to lift a load. A cable is used, that cable is tied to the load, and it is moved from one place to another with the help of cranes. So here what type of cable is used, what should be the thickness of this cable, depends on the elastic behavior as well as how much the load it has to lift. So now suppose if you want to lift 1,000 kg load, then we know that the wire or a cable which has to be used, that should not be thin, it should be thicker wire. But if we use a thick wire, then what will happen? It will be rigid, it will not be flexible. So a one thick wire is not used to lift the load. Thin wires, many thin wires, they were braided together and a rope is made, so that that rope remains flexible. Because if a one thick wire is used having the large cross sectional area, then that will not bend easily. And we know that the wire which is used to lift the road should easily bend, it should be flexible. So rather than using one thick wire, many thin wires, they were braided together to make a single rope, and that type of rope is used to lift the load. So that concept is shown here. With the help of calculation it is explained. So I want you to go through this, you will be easily able to understand. Then given that for the construction of a bridge, we know that bridge is constructed in such a way that the heavy vehicles which are passing over the bridge, that part, that slab has to remain stable, it should not bend in this way. You can see here the bending is shown. This bending is denoted by this delta sign, and this is known as sagging. If the bending takes place, then that is known as sagging. So to reduce the sagging, what we can do? So here a formula is given. This is a empirical formula, that is direct formula, no derivation is there. So this sagging depends on the length, breadth and thickness of the slab. So if the length is more, what will happen? The sagging will be more. So to reduce the sagging, we can decrease the length or we can increase the breadth or the thickness. But you can see here on thickness, D is the thickness actually here. So if we will increase the thickness by a little, then sagging will reduce considerably because it is cube of that. So rather than increasing the breadth, we can increase the thickness to reduce the sagging. For example, if you take a plain sheet of metal, if you put a support here and if you put some load here, then what will happen? This plain sheet will bend. So what you can to reduce the bending? You can increase the thickness of this plate. So when you will increase this thickness, the bending will be reduced. Or you can increase the width. But rather than increasing the width, if you will increase the thickness, then that will be better because thickness is cube of that and it is inversely proportional to this delta. So that concept is shown here. Also, the shape in the engineering. We know that for a metal strip, if we will apply the force, then what will happen? If the force is large, this strip will bend in this way. Suppose if you have taken a stick, a thin stick, and if you will apply the force from this ends, what will happen? It will bend in this way or in this way. And this bending, vertical bending, is known as buckling. So this effect is called buckling effect. This effect is called sagging, and here this is horizontal and here this is vertical. So this is called buckling effect. So to reduce the buckling effect, what is done? Here this shape is kept in the form of I. You can see here. So if this type of shape is kept, then this buckling effect will not take place. You might have observed the railway tracks. We know that a train and the bogies connected with the train, they are quite heavy, and when they move on a railway track, this buckling effect can take place. But the cross section of the railway line which are used, their shape is kept I shaped. Their shape is I shaped, and due to this type of I shaped, this type of buckling or bending will not take place. Even in the bridges, the pillars they were used are of this shape and not of this shape. You can see at the base and at the top, the I shape is kept so that it can bear a heavy load without any buckling effect. So this type of construction designs are used in engineering. Also, here given the example of Mount Everest. The height of Mount Everest cannot be more than 10 kilometer. The actual height of Mount Everest at present is something 8.85 kilometer. But considering the elastic limit of the rocks at the base, we can imagine the maximum height to be up to 10 kilometer. So it is clear that the Mount Everest cannot be of the height larger than the 10 kilometer. because if the height will increase, then what will happen? The stones or the rocks which are on the base of the mountain, they will cross the elastic limit and they will break into pieces. And so the height cannot be more than 10 kilometer, and actual height is 8.85 kilometer. So this type of examples are given here. So just go through the textbook, read each and every line, and you will be able to understand. So here we complete our chapter.